8th grade Open Up Resources, Illustrative Mathematics, Unit 7, Lesson 8, numbers 1 through 4. 2 to the power of 8 times 2 to the power of 9. The bases are the same, but the exponents are different. We can look at 2 to the power of 8 as 2 times itself 8 different times. And we can look at 2 to the power of 9 as 2 times itself 9 different times. 2 to the power of 8 times 2 to the power of 9 equals 2 to the power of 17. Since the bases are the same, we can keep the base as 2 and add the exponents. 8 plus 9 is 17, so 2 to the power of 8 times 2 to the power of 9 equals 2 to the power of 17. Now let's try one that has the exponents the same, but the bases are different. 8 to the power of 2 times 9 to the power of 2. Since the exponents are the same, we can put the exponent on the outside of the parentheses and put the bases on the inside. 8 times 9 equals 72. So 8 to the second power times 9 to the second power equals 72 to the second power. So if the bases are different but the exponents are the same, we can multiply the bases and keep the exponent the same. 8 squared times 9 squared equals 72 squared. Number 2. Multiplying exponents. Find x, y, and z if 3 times 5 all to the 4th power times 2 times 3 all to the 5th power times 2 times 5 all to the 7th power equals 2 to the power of x times 3 to the power of y times 5 to the power of z. Take a moment to look at it and think of a strategy. Press pause if you'd like more time to think about it. One helpful thing that I noticed is that the base numbers are only 2, 3, and 5. Let's start with a 2 and see how many times we have the base number 2 and the number of their exponents. We can see that we have the base number 2 twice. The first base number 2 has the exponent 5, and the second base number 2 has the exponent 7, and 5 plus 7 is 12. Or 2 to the 5th power times 2 to the 7th power equals 2 to the 12th power. Now let's move on to the next base, 3. So we'll look to see how many different times we see a 3 as the base in the parentheses. I see two base numbers, 3. The first base number 3 has a 4 as its exponent, and the second base number 3 has a 5 as its exponent. 4 plus 5 equals 9. Or 3 to the power of 4 times 3 to the power of 5 equals 3 to the power of 9. So finally, let's look for the base number 5. Why don't you try this one on your own? Look to see how many times you see the base number 5, what their exponents are, and add the exponents together. Press pause if you'd like more time to find the answer on your own. I can see that there's two base number 5s. The first base number 5 has an exponent of 4, and the second base number 5 has an exponent of 7. And 4 plus 7 equals 11. Or 5 to the power of 4 times 5 to the power of 7 equals 5 to the power of 11. X equals 12, y equals 9, and z equals 11. Let's solve this a different way. First, let's use the distributive property and bring the exponents to all the base numbers inside the parentheses. Then we can combine the like terms. 2 to the power of 5 times 2 to the power of 7 equals 2 to the power of 12. 3 to the 4th power times 3 to the 5th power is 3 to the 9th power. 5 to the 4th power times 5 to the 7th power is 5 to the 11th power. In this case, the value for x is 12, the value for y is 9, and the value for z is 11. Number 3, multiplying exponents. This example shows the multiplication of exponents. You'll notice an exponent on the outside of the parentheses. This exponent goes with each of the bases on the inside of the parentheses. For example, 3 to the power of 3 times 5 to the power of 3. And you noticed once I moved that exponent to the bases on the inside of the parentheses, I was able to remove the parentheses. And since this expression is only dealing with multiplication, we can rearrange the order of the terms. This 5 is actually 5 to the power of 1. When I combine 5 to the power of 1 with 5 to the power of 3, it becomes 5 to the power of 4. I combined those two terms for a reason. And that reason is now I can multiply 5 to the 4th power times 2 to the 4th power. Again, I can rearrange the terms to make this easier for me. I know that 2 to the 4th power times 5 to the 4th power is 10 to the 4th power. To illustrate why, I can take their common factor, the power of 4, and put it outside the parentheses. And 2 times 5 all to the power of 4 is equivalent to 10 to the power of 4. Now the expression looks a little bit different. 3 to the power of 3 times 10 to the power of 4. Let's take a quick look to see how we got to this point. 3 times 3 times 3 equals 27, and 10 times 10 times 10 times 10 equals 10,000, and 27 times 10,000 equals 270,000. Let's try another expression. This example involves multiplying exponents and dividing by a term with an exponent. First, I'll use the distributive property to distribute the exponents from outside the parentheses to the terms that are inside the parentheses. And after completing that step, I can remove the parentheses altogether. I'm doing this so I can reorder the terms. Notice that the divisor, or the denominator, is 3 to the power of 2. Now look at the dividend, or the numerator, and you'll also notice a 3 to the power of 2. That's the same as 3 to the power of 2 divided by 3 to the power of 2, which is 1. Essentially, they've canceled each other out. I notice terms with the base of 5 and 2. I like that because 5 times 2 equals 10. 5 to the power of 2 times 2 to the power of 2 is the same as 5 times 2 all to the power of 2. Which of the remaining pair of terms would you match with this 5 to the power of 2 to make it easier for you? I would choose the term that has 2 as its base because 5 times 2 equals 10, and that makes it easier for me. But I am going to add just a bit of a challenge. I'm going to take that exponent that's attached to the 5 inside the parentheses, and I'm going to move it outside of the parentheses. Look at the two remaining terms at the top of the screen, 2 to the 3rd power and 3 to the 2nd power. It looks like 3 to the 2nd power is the only term that I can choose to use with the 5 inside the set of the parentheses because the exponent on the outside of the parentheses is a 2. But since I'd like to use the term with a base of 2, watch what I do. Let me show you that again. I'm taking the 2 to the power of 3 and I'm changing it to 2 to the power of 2 times 2 to the power of 1. I leave 2 to the power of 1 up there with 3 to the power of 2. So now inside the parentheses I have 5 times 2 all to the power of 2. Let's look again. 2 to the power of 3 becomes 2 to the power of 2 times 2 to the power of 1. And I take the 2 to the power of 2 and I insert it into the parentheses. Now we have 5 times 2, all to the power of 2. 5 times 2 is 10, and 10 to the second power is 100. 100 times 100 is 10,000. 3 to the second power, or 3 times 3, is 9. 2 times 9 is 18. I'll let you take it from here, but essentially, it's 10,000 times 18 times 1 divided by 1. Hopefully your answer is 180,000. Number 4. The cost of cheese at 3 stores is a function of the weight of the cheese. The cheese is not prepackaged, so a customer can buy any amount of cheese. Right away I notice some differences. Store A sells the cheese for A dollars per pound, but Store B sells the same cheese for B dollars per pound, and a customer has a coupon for $5 off the total price at that store. So that's a coupon that takes $5 off of the price. Store C is an online store selling the same cheese at C dollar per pound, but with a $10 delivery fee. So they're tacking on a $10 fee for every order. When I look at this graph, right away I see this line that starts at 0 pounds of cheese at $10. So that makes me think that this might be Store C, the store that charges a delivery fee of $10. At the bottom of the graph, you'll find the horizontal axis, and the horizontal axis represents the weight of the cheese in pounds. And along the left side of the graph, you'll find the vertical axis, which represents the cost in dollars. At the bottom left corner of the graph, you'll find the origin. That represents 0 pounds of cheese and 0 cost in dollars. Directly above the origin, I labeled a point that represents $10 for 0 pounds of cheese. And you can see the cost of cheese increasing as the number of pounds increase. Look at the horizontal axis, the weight of cheese. Between 4 and 6, you'll find 5 pounds. 5 pounds of cheese at this particular store costs exactly between $20 and $30, which would be $25. So in this case, or at this store, 5 pounds of cheese costs $25. I could write an equation or a function that would help me calculate how much it would cost to buy a particular amount of cheese at this store. 5 times what number plus 10 equals 25. Since we're talking about line J, I'll replace the question mark with a J. This is a two-step equation. I'd like to find the value for J, and I'll do that by getting the J by itself on the left-hand side of the equal sign. First, I'll start by getting rid of the positive 10, and I'll subtract 10 from both sides. 10 minus 10 and 25 minus 10. 10 minus 10 cancels each other out, so we have 5j equals 25 minus 10, and 25 minus 10 is 15. Since there's only one step left, we can call this a one-step equation. 5j equals 15. I still need to get the j alone, so 5 divided by 5 and 15 divided by 5. 5j divided by 5 is 1j, and 1j is the same as j, and 15 divided by 5 is 3. J equals 3. J represents Store C. Store C sells cheese for $3 per pound. Now let's go back to the graph and look at line K. This is interesting because 1 pound of cheese costs $0 and 2 pounds of cheese costs $5. That makes me think that if you used a coupon for $5 off of 1 pound, that you could get 1 pound of cheese for $0. Line K must represent Store B, the store that had a $5 coupon. 1 pound would be free, 2 pounds would be $5, 3 pounds would be $10, 4 pounds would be $15, Let's use that as our equation or our function. 4 times what number minus $5 equals $15. Since this equation or function represents line K, I replace the question mark with K. Now it reads 4K minus 5 equals 15. This is a two-step equation, and in order to get the K by itself, first I need to add 5 to both sides. I'm adding 5 to both sides to cancel out that negative 5. So when I add 5 to negative 5, it cancels it out. 4K minus 5 plus 5 equals 15 plus 5. 4K minus 5 plus 5 is 4K, and 15 plus 5 is 20. So now it reads 4K equals 20. Now it's a one-step equation. All that we have to do now is get the K by itself. I need to divide both sides by 4. 4K divided by 4 and 20 divided by 4. 4K divided by 4 equals 1K, or just K. And 20 divided by 4 equals 5. So now it reads K equals 5. Line K represents a store that would sell cheese for $5 a pound. Line K represents store B. Store B sells cheese for $5 per pound. That leaves store A, and store A sells cheese for $8 per pound. Let's go back to the graph and take a look at the remaining line so that we can identify what exactly is $8 per pound. Look at line L and the point where it intersects 5 pounds of cheese and $20. We can write a one-step equation to represent this. 5 times what number equals $20? Since we're dealing with line L, I'll replace the question mark with the letter L. Now the function or the equation reads 5L equals 20. With one step, we should be able to solve for L. Divide both sides by 5. 5L divided by 5 is 1L, which is the same as L. And 20 divided by 5 is 4. L equals 4. Line L represents store A. Store A sells cheese for $4 per pound. Match stores A, B, and C with graphs J, K, and L. Store A matches with line L. Store B matches with line K. Store C matches with line J. How much does each store charge for the cheese per pound? Store A charges $4 per pound, Store B charges $5 per pound, and Store C charges $3 per pound. How many pounds of cheese does the coupon for Store B pay for? For Store B, a $5 coupon would pay for 1 pound of cheese, because at Store B, a pound of cheese costs $5, the same amount as the coupon. Which store has the lowest price for a half pound of cheese? Look at line K. With a $5 coupon, 1 pound of cheese would cost $0. 1 pound for Store B is $0, so a half a pound would be $0. Store B has the lowest price for a half a pound of cheese. If a customer wants to buy 5 pounds of cheese for a party, which store has the lowest price? Look at lines J and K. Do you see where they intersect? They intersect exactly at the point of 5 pounds of cheese and $20. And above that, you can see line J represents 5 pounds of cheese at $25. Lines L and K represents stores A and B. They both have the lowest price for 5 pounds of cheese. How many pounds of cheese would a customer need to order to make Store C a good option? Line J represents Store C. Follow line J left to right. It intersects line L, and then it finally intersects line K at 10 pounds of cheese. What this means, if the customer were to buy more than 10 pounds of cheese, line L or Store C would be the best option. Ordering more than 10 pounds makes Store C the best option. You can check out more illustrative mathematics tutorials. Read the video description for more info. If it's worth watching, it's worth subscribing. So please take a moment to become a subscriber. I really appreciate it. Thanks for watching. Good.